Welcome everybody from the Hereford and Worcester committee for our lecture tonight by Sophie Allan. Sophie is the National Space Academy's lead teacher and is based lead physics teacher, and she's based at the National Space Centre in Leicester. She studied physics and astrophysics at the University of Leicester and then became a specialist physics teacher. She continues to teach A-level physics as part of a space engineering course, for which the course has now been awarded the Queen's Anniversary Award for the work they're doing. As well as developing and teaching programmes for the National Space Academy, she's also involved in the creation of space-related resources for the Association of Science and Discovery Centre projects, Explore Your Universe and Destination Space. Sophie has produced materials for European Space Agency schools activities, including work with the French astronaut Thomas Pesquet on his International Space Station mission Proxima, albeit sadly not in space. In fact, I think that almost all space-related schools resources must have Sophie's name on them. And I'd like now to just give a plug for the book that she's just written, which is a DK book called the Solar System book, and you can buy it from Amazon and other online bookshops. It's aimed for ages 7 to 9, and I'll be buying one tonight. Sophie is passionate about her work and an excellent science communicator, and this lecture is aimed as a follow-up to her previous 2022 lecture on the build and setup of the James Webb Telescope, and she will now be able to share her knowledge of subsequent discoveries by the James Webb Telescope with a much wider audience. Welcome, Sophie.
Fantastic. Thank you so much, Margaret, and thank you for that wonderful introduction. And hello, everybody at home. I'm really excited to get the chance to talk to you about some of the amazing things that the Webb Telescope has shown us. And in order to help me do this, I'm just going to share my screen. Now, I might go relatively quickly in places here. I have a lot to update you on, but I'm going to start off just with a little bit of a recap and a reintroduction to what the James Webb Space Telescope is. I'll be referring to it as the Webb Telescope over the course of this talk, just for brevity's sake. But it's a project and a mission that I've been involved in on the education side since around about 2008, although back then we were told that it would be launching in 2013 and there were loads and loads of delays. But the Webb Telescope has really reinvigorated public interest in astronomy, and for very good reason. It's an incredible device. It is doing huge amounts, and just in its first year or two of observations, it is rewriting the science books in some areas and giving us incredible images. It's an ESA-NASA collaboration, and it was first kind of posited in 1996 as the next generation telescope. We knew, even though Hubble was being tremendously successful at that point, we knew that we were going to need a follow-up to the Hubble Space Telescope, and we know that it takes decades to develop, build, test, launch, calibrate, and then start taking readings with space telescopes. So we had to start early on this. Its initial launch was planned for 2007, but things very rarely go to plan or to time in the space industry. And it does have an expected total running cost of 8.8 billion over the course of its life. But we have to remember that this was in development from 1996 and will, hopefully, all going well, be sending us data for the next 20 years. So that's an awfully long time frame, and a lot of that cost is actually going towards, you know, the salaries and the money for research and things like that of the researchers, the engineers, and the people working on these projects. So just be wary when people say how much a project like this costs. That hasn't all just gone into the telescope. That has gone into everything involved in building, producing, researching, and running the program. And we should, all being well, get 20 years of observations out of it. And the data from this will be used for decades, even beyond then. It goes for an incredibly long time and is revolutionizing everything. Now, I've got a massive soft spot in my heart for the Hubble Space Telescope. It has revolutionized our understanding of the universe. But when you start comparing the Webb telescope to it, they are two very, very different beasts. The first thing to note about the Webb telescope is it is big. If you imagine the size of a tennis court, well, that's about the size of the Webb telescope. In fact, it's so big that we didn't have a launcher big enough to launch it into space. It had to launch folded up in a kind of technological space origami. And with all these hundreds of moving, unfolding parts, there was a lot of worry that we weren't going to be able to get a flawless deployment. Just to give you an idea of how big it is, you can see here, we have these hexagonal structures. Well, here's a human polishing and checking the actuators on just 6 of these hexagons. In fact, it's a massive 6.5 meter across mirror, much, much bigger than the Hubble Space Telescope's primary mirror. And that's important because the mirror of your telescope basically acts like a light bucket. The aperture is what we use to collect the photons, the little particles of light energy that are coming towards us from distant stars, galaxies, and nebula. And the bigger your aperture, or the bigger your mirror is, the more information you are able to collect. And so this allows us to have a better resolution on our telescope. But there is another reason why it's so big. Now, we are familiar with the idea of visible light, and I know to some of you I might be sounding like I'm teaching you to suck eggs, but there might be some people who don't know this. So very briefly, visible light has lots of different colors in it. Yeah, we see this as a rainbow. You can split white visible light into all the different colors. But there are different types of light that sit on either end of that rainbow. We call all these different types of light the electromagnetic spectrum. And what defines, in the case of visible light, the color, and in the case of the other parts of the EM spectrum, things like its energy, is what we call the wavelength, or how long one full wave is. Now, the James Webb Space Telescope is an infrared telescope. This means that it's looking at longer wavelengths of light. And it turns out, and I teach this to my A-level students, that the longer the wavelength of light you're using is, the bigger a telescope you need to be able to get the same level of detail. We call it the Rayleigh criterion. So because our space telescope is using a longer wavelength of light, we need to have it bigger in the first place. But the Webb telescope is going one step further. It's not just scaled up to be on a par with the Hubble Space Telescope, it's got a better resolution than the Hubble Space Telescope. Now, the mirror itself is made up of 18 beryllium gold-plated hexagonal mirror segments. And this is because the gold is optimized for reflecting that infrared light. So even though we often think of infrared as being referred to and associated with heat, we know that heat can be reflected. We know that infrared can be reflected. And it turns out that gold is the perfect reflective surface for our mirror. And in order to do its science, it has got 4 instruments on board. It's got 3 that are looking at a type of infrared light called near infrared, the narrow band that is really close to the visible light spectrum. Now, these 3 devices are really, really good for looking at cooler stars, and they're also really helpful because they can peer through dust and gas clouds. And the instrument that I get really excited about, because it was actually built here in the UK, is the instrument MIRI, the mid-infrared instrument. MIRI is capable of looking at slightly longer wavelengths of light. And it's really good for actually looking at the structure of dust and gas, looking at filaments and areas that will eventually condense down to become star-forming regions. It's also the wavelength that we can use for looking at planets, comets, asteroids, and looking at planet-forming regions around young stars called protoplanetary disks. So by having 4 different instruments, the Webb telescope is able to image, it's able to take readings about the materials in gases and in the objects that we're observing. And each of those individual images is then also, instruments is able to do other things as well. So it's almost like a Swiss Army knife full of Swiss Army knives. You're able to look at multiple objects at the same time. You're able to analyze them in different ways to build up a really nice, complete picture of our universe. And the really important thing about the Webb telescope and astronomy in general is that it's basically time travel. Light is the fastest thing in our universe, but it does have a speed limit. And this means that it takes time to get from one point to another. When you're looking at the sun, the light that we see from the sun is as it was 8 minutes ago. When we're looking at stars, for example, our closest star, Proxima Centauri, we're seeing the light there as it was about 4.18 years ago. So we're looking back in time, 4.18 years. And the further away we look in space, the further back in time we are looking. So this means that by having a more powerful telescope, we're literally able to look further back in time, and we're able to find out more about our early universe. And that's important for a lot of reasons. We're trying to figure out what's happening with our universe at the moment. And in order to do that, we have to build models. The more we know about how our universe began, the more we are able to build those models up, input that data, and get an idea of where we're headed. But there's another big reason why the Webb telescope is an infrared telescope. And that's due to something called cosmological redshift. Now, what I mean by that is every direction we look in, once we start looking a far enough distance, we see that things are becoming redder. This is a Hubble image of some of the oldest galaxies that the Hubble Space Telescope was able to image. And you can see that they're all appearing very red on the screen. Now, the reason for that is because of something called redshift. As an object moves away, the light from that object gets stretched out, it becomes a longer wavelength, and so it moves towards the red part of the spectrum. Now, for the very oldest objects in our universe, the light coming from them has been so far redshifted that it's not even visibly red anymore. It's been shifted right into the infrared. So if we want to be able to look to just a few 100 million years after the Big Bang, right back in time, we need an incredibly powerful infrared telescope to do this. And that is what the James Webb Space Telescope is. So we have a very powerful telescope that can look back in time further than anything we've built so far, is incredibly high resolution, is a Swiss Army knife of different devices that can look and measure and store different information all at once. And infrared itself has some interesting qualities. Now, the Hubble Space Telescope produced beautiful visible images. And at this point, it's worth pointing out that the images that I show you in the rest of this presentation from the Webb telescope, they look very pretty, but they've been made to look that way because the infrared that we're getting to build those images, even though we store that data in the same way, isn't visible to the human eye. So unlike this image here of the pillars of creation that was taken by the Hubble Space Telescope, we don't get the same kind of beautiful images. What the scientists do is they assign colors to the information we're getting. They'll pick certain colors for hydrogen, for helium, for ionized gases, for all of the different things that we're looking at to give the picture meaning and so that we can connect with it on an emotional and a personal level. So the images that we get in infrared are a bit different, but they can tell us so much more. With this image of the pillars of creation from the Hubble Space Telescope, we can see a few stars in the nebula. But as soon as we look in the near infrared, we can suddenly see so much more detail. The dust in that nebula becomes transparent, and we can see all of the many, many stars in this star-forming region. It's absolutely breathtaking. And that's important. If we want to know about how stars form, we have to be able to peek through those nebulae. Now, this image here was taken by the Hubble Space Telescope's near-infrared camera. While it wasn't a visible light camera, it did have near-infrared capabilities. as you will see later on, the images that we got from the Webb telescope so far have blown these kind of images out of the water. So where do I begin? There is so much that I can talk about in this session, and I've really had to work quite hard to narrow down the science and the images that I'm going to talk about. But I did want to start off with a health update on the Webb telescope. Now, the Webb telescope is much further away from the Earth than the Hubble Space Telescope is. And this means that we won't be able to go and fix it if something goes wrong. We'll look into why a little bit later on. So when problems arise, we have to be able to fix them on the fly. Now, there have been two relatively annoying problems that have occurred with the Webb telescope. The first is with MIRI. MIRI is designed to operate in 4 modes of operation. So basically looking at 4 wavelength bands of mid-infrared. And we discovered that there was a problem with one of these modes of operation. We weren't getting clear data. It was dragging, there was a latency to it. It wasn't really working. So it had to be shut down, that particular mode of operation. And the scientists and engineers and computer scientists had to research what the problem was, figure out how to fix it, write the code that would allow it to be reset and fixed, send that to the Webb telescope, and luckily it did work. And now the MIRI instrument is back at full operating capacity. The other big issue that we had with the Webb telescope is this. So this is showing 2 images of the mirror array. On the left-hand side, we can see that everything is working well. Okay, we can see that the individual segments are all as they should be, aligned properly. We've got a nice mirror surface. The image on the left was taken on the Earth prior to launch. On the right-hand side, if you look down towards the bottom right corner, you can see that we have what looks like a heat spot, a bright spot on one of the mirror segments. Now that's actually showing a deflection in that mirror segment, and that was caused by a micrometeorite impact. Now we know that the Webb telescope is going to get slowly battered in space. Space is not a perfect vacuum, material is flying around. But to get hit by a fairly big denting object relatively early on in the observational period was a big worry. Now, luckily, the damage that was incurred by this, it can be corrected for with positioning and with some of the software that's being used with the telescope. But we do know that this is going to be an issue going forward for the Space Telescope. We saw it with the Hubble Space Telescope, and we'll see it with this one as well. One of the ways that we're now counteracting it is early on in the Webb telescope's observations, it was pointing at anywhere it wanted to in the sky, or anywhere the scientists wanted it to point in the sky. Now we're being a little bit more conservative with that, and we are effectively pointing our telescope downstream of its motion. And that means that the rest of the telescope can almost act as a bit of a shield from these micrometeorites that are coming in that direction. The idea being that the mirror isn't going to be at the front moving that way in the opposite direction of a meteorite that might impact with it. The idea being that you're minimizing the energy of that meteorite impact. And this should hopefully prolong the life of the mirror. But actually, for such a complex and complicated telescope, for those to be the only 2 really main problems that we've had, and they've been both solvable, is really quite phenomenal. So that's an update on the health of the Webb telescope. And as we go through, if you do have questions, do feel free to pop them in the chat. Hopefully I'll have some time at the end to take a look at them. I will mention I am not an expert on any one area of the Webb telescope. It's a project that I've been working on for a long time from an educational standpoint, and I'm a little bit obsessed. But there might be some questions, if they're particularly technical, that I might have to point you in a direction of someone who might be better versed to answer that. But I'm pretty sure for a presentation where we're looking at what the Webb telescope has achieved so far, you've come here to look at some of the amazing images and the science that we are learning from these images. So I've split this up into a few different sections. And the first section that we're going to look at is just some of the incredible early images and some of the stunning phenomena that the Webb telescope has started to unveil for us. So this image here is probably still one of the most iconic images that has come from the Webb telescope, sorry. It's also one of the first that was released. This is called the SMACS 0723 Galaxy Cluster Deep Field. Now, as I go through this presentation, there are a lot of non-snazzy names. And this image was taken in the same way that the Hubble Ultra Deep Field image was taken, by looking at a tiny, what appeared to the naked eye to be empty patch of sky. And in a relatively short exposure time, this is the image that came back to us. Now, right in the middle of this image, there's a galaxy cluster, a collection of galaxies close to each other in space that have a large amount of gravity. Other notable things to see here is you'll see that the brightest stars in this image, or the brightest objects in this image, have a very distinctive six-pointed star shape with an extra little bit coming off. That six-pointedness of these images is unique to the Webb telescope. It's what we call a diffraction effect, or basically the light is bending around as it passes through the telescope. And due to the hexagonal nature of the structure of the telescope, Webb gives you a unique six-pointed star. The additional little bit there is actually from one of the support struts on the Webb telescope. But what else does this image show us? Well, first of all, here's a comparison of the same patch of sky with what we call a composite, or a merger of images from other space telescopes prior to Webb. And you can see that in the composite, yes, you can see the big stars, but it's all much duller, much less focused, much less resolved. So instantly we're seeing that the Webb telescope is showing us more objects at better resolution with better detail. And one thing that you really couldn't see in the original image, if I zoom in on this central galaxy cluster, is what I've highlighted here. Here you can see 4 individual objects in the image, and they're actually all the same object. These are images of a galaxy that is behind this big cluster of galaxies. So in the middle of this image, we have this big galaxy cluster, and then right behind it, there is another galaxy. Why are we seeing 4 of it? Well, one of the things that the Webb telescope is allowing us to do is actually to use the gravity of large, massive objects, and the fact that the light from objects behind it will be bent by this gravitational field and pass around it to our eyes. It means that we can see objects behind that galaxy cluster. Not only that, because the light paths will all follow slightly different paths in slightly different directions and slightly different times, we get multiple versions of the same image. Now, this has been really, really useful for a variety of reasons. But possibly the most useful thing that we've got from this has been in looking at lensed galaxies. We've been lucky enough to see a supernova. So this here is a supernova that was observed by, within a lensed galaxy. And we take supernova sightings really seriously. They are relatively rare events from an astronomical capturing point of view. So as soon as this was observed, the science team applied for what we call a time-critical director's discretionary program. And that means that scientists can say, look, there's something amazing happening right now in this bit of space. I need us to pause other observations so that we can really focus on this time-critical thing. So this supernova was actually being seen in a galaxy that in 2016, the Hubble Space Telescope had seen a supernova. It's a different supernova, but in the same galaxy. That in itself is really remarkable. But what's fantastic is the Hubble image that we were able to see, we got there late. We were seeing the tail end of this supernova with a telescope that didn't have as good a resolution as the Webb telescope. However, with the Webb telescope, we got there early. We were seeing very bright near the beginning of this supernova event. Not only that, because the light coming from this supernova was traveling slightly different distances due to our position relative to the galaxy cluster, we're actually seeing those different images of the supernova circled in this picture on the right. We're seeing them at slightly different time delays. So we're being able to get a time-shifted view of the same supernova, giving us extra data and more information. This is a tremendously exciting thing to happen because it's pretty rare to be able to observe a supernova, and we want to find out more about them. So to have this opportunity, we've really, really lucked out. Other things that we've seen, merging galaxies. So here we have got two galaxies, collectively they're called ARP220, and they are merging together about 250 million light years away from the Earth in the constellation of Serpens, the Serpent. This is about as bright a thing as the Webb telescope can look at. You can see that the image is looking actually quite grainy and fuzzy. And that's because these two galaxies merging together are doing so with the light of 1 billion or maybe even 1 trillion suns. As these two galaxies merge together, the heat generated and the forces involved are triggering star formation within both galaxies. That's producing an enormous amount of light that's almost overwhelming the sensors on the Webb telescope. And that's not the only galaxy merger that we've seen. In this video, which I will start playing now, we are going to zoom in on a galaxy merger called IIZ 500. IIZ. This is about 500 million light years away from the Earth. And I wanted to show you this video to give you the idea of just how small a patch of sky we are dealing with when we're looking at these galaxy mergers. This is in the constellation Delphinus. And this we wouldn't be able to see invisible. Even if the Hubble Space Telescope had the resolution necessary, we wouldn't be able to see this because the dust that is surrounding these two galaxies would be impenetrable to visible light. But in the infrared, we can start to see the details of these two merging galaxies. Why is that important? Well, perhaps selfishly for us, and here's a more noticeable image for you, this has real relevance to our galaxy because our Milky Way is on a collision course with the Andromeda galaxy. Now, this isn't going to happen for billions of years. We've got a long time to wait for it to happen, but it is going to happen. And we scientifically want to know what is going to be the result of our galaxy colliding with another one. To be able to see that and witness it is really, really interesting and helpful to us. And so instantly, just with these images, we have increased our understanding of supernova. We have increased our understanding of merging, colliding galaxies that's relevant to our own. And then another weird object that we've been able to see is WR140, which is actually one of many different Wolf-Rayet stars. Now, Wolf-Rayet stars are very, very dynamic stars that are coming towards the end of their life. A star is in a constant battle between the gravitational force trying to pull it in on itself and something called radiation pressure from the fusion going on inside the star pushing back out. Now, when a star gets towards the end of its life, when it's running out of its primary fuel, then you start to get an upset in this balance, this equilibrium. And so the star starts trying to collapse, heats up, expands, and becomes a little bit variable. This Wolf-Rayet star is doing so in such a way, and with a companion object around it as well, that if I play the video here, as they interact, and as it's also pulsing, material is being given off by the Wolf-Rayet star. And as the companion object passes through that cloud, it disturbs it. And so if you look at the image on the left that looks almost like tree rings, you can see we're getting this concentric, almost circular, although this one's a bit odd because it's a bit more square, structure. And that's showing this periodic, very regular interaction between the Wolf-Rayet star and its companion. And just to be able to see that is fascinating, because we're seeing the death throes of a star here and its interaction with another companion. And it's a really cool image. Another reason why I included that there. So in terms of kind of initial images that were released and initial information, we've already seen a lot of very cool stuff. But there are even stranger objects and more, in terms of physics and science, more weird, complicated objects that the Webb telescope has opened up for us. We've seen evidence of really, really early supermassive black holes. Now, typically, supermassive black holes in our nearby universe are very, very large black holes that sit at the center of galaxies. And they've had an incredibly large amount of time to gather, to accrete, to collect material, allowing their mass to get more and more and more, allowing them to become supermassive. Now, if we look back into the early universe at some of the earliest galaxies that the Webb telescope has been looking at, it's weird that we're seeing these supermassive black holes, and some of them are enormous. We're talking about black holes that weigh about 1 billion times the mass of our own sun, 1 billion times. And we see even more smaller mass versions of these. Now, these all date to about 800 million years after the Big Bang, very early in our universe's life. And that doesn't really make sense, because in that time frame, there shouldn't have been enough time for those black holes to gather enough material to have become supermassive black holes. These kind of observations are causing us to have to think and rethink some of our science about how these objects form. And all of this evidence just allows us to have a more accurate picture, to feed better information to our computers and to our scientists, to get a much better understanding and predictive effect when it comes to looking at these phenomena. We are also seeing things called jumbos. Now, I love this name, always makes me think of the Disney elephant. Now, jumbos are basically Jupiter mass binary objects. That's what jumbo stands for. And they're weird. So jumbos, deep in the heart of the Orion Nebula, the M42 object, we found at least 40 roughly Jupiter-sized objects with a binary, a secondary companion. So these are two large objects that are just moving together through the Orion Nebula. And that is weird, because they're not a part of a solar system. None of our star formation theories end up leading to the creation of objects this small. They're too small to be stars. They're basically giant binary planet systems that are tootling along through the Orion Nebula. And if they had formed in stellar disks like the planets in our solar systems have, then they shouldn't be able to survive the kind of force that would be needed to eject them from a solar system and to allow them to be passing through and wandering through the Orion Nebula. So effectively, by observing these objects, we're having to come up with new theories about planetary formation and about how objects can be created in space. They're really, really interesting, weird objects. We've had some stunning images of the Cassiopeia A supernova remnant. So just 340 years ago, light from an exploding star first reached Earth from this supernova remnant. And today we see the material that was blown out by this cataclysmic collision. It's absolutely stunning, but for the first time, thanks to the Webb telescope, we're being able to get a real view of the structure of this remnant. As we zoom in, you can see that we have bright orange areas and light pink. That's showing the inner shell of the supernova remnant. But JWST, the Webb telescope, also detected tiny filaments running through, so filament structures running through the supernova remnant. Now, filament structures are typically where you get things like star formation occurring, but also by looking at effectively the shock patterns of these filaments, we can get an idea of the physics behind the collapse that caused and led to this supernova. We see knots of gas made of sulfur, oxygen, argon, and we also get neon. And that would have been from the actual star itself. So we're seeing the way that material from that exploded supernova has seeded throughout the supernova remnant. And by studying this in more detail and understanding the kind of molecular distribution that you get after these supernova, we can start to get a better idea of how new stars form after a supernova and how planetary systems form with these new molecular materials produced in a supernova event. And this, if we zoom in, you can actually see of the Cas-A, that filament structure I was talking about. Then a really weird object that we've been studying with the Webb telescope are brown dwarfs. I always feel a bit sorry for brown dwarfs. Sometimes they're referred to as failed stars. They're somewhere between a gas giant planet or an ice giant planet and a very small dwarf star. And effectively, they are objects, we think, that were on the path to becoming a star, but were never able to gather enough material for fusion to take place. Instead, they have just been sat there, these poor little failed stars in space. Now, this one here is really interesting because about 72 light years away from the Earth, it's relatively close to us. And this is about 19 times more massive than Jupiter. Now, Jupiter's a big gas giant planet, but this is a super Jupiter, if you were to think of it in planetary terms. What's interesting about this, however, is not the gaseous nature of it, but the fact that when we analyze the spectra coming from this brown dwarf, we see effectively it's covered in sand clouds. We've seen silicate material, and it would have to be hot. It would have to be very hot, vaporized sand. But we see clouds in this brown dwarf that are made of vaporized sand material. And that's really, really strange. I mean, to get to that temperature, to vaporize the sand and then have them forming cloud material. This is new planetary science in action. And the longer we look and the longer we observe other brown dwarfs, we want to find out, is this common? Do most brown dwarfs have sand clouds? You know, is vaporized silica a common thing, or is it unique and weird to this one? So every new thing we discover leads to a new list of objects that we want to be observing, a new set of criteria that we are setting ourselves in terms of looking at our universe. The weirdness doesn't stop there. This is actually the spectra from that brown dwarf. I'll go into a bit more detail about spectra in a minute, but effectively these are molecular or atomic fingerprints that we can use and find from the visible or the infrared light that is being emitted by planets and stars and brown dwarfs. And we can see that the Webb telescope has been able to tell us there's water on this brown dwarf, some carbon monoxide, some methane, but the silicates is the weird one, because in order to see it like that, it needs to be in its gaseous form, and that is what we are getting through. But brown dwarfs are not just weird because at least one of them has sand clouds. Brown dwarf W1935, I told you there were some catchy names in this, is another strange brown dwarf that the Webb telescope has imaged and studied. Now, this brown dwarf has got large amounts of methane being emitted in the atmosphere. And that's a little bit weird because typically in things like gas giants here on Earth, we see methane production in the upper atmosphere associated with auroral effects, with aurora being produced. Why is it so weird that we would see that on this brown dwarf star then? Well, here on Earth, predominantly the aurora are produced due to interaction between the solar wind from our star, the sun, particularly when you get coronal mass ejections, large outpourings of charged particles. Those charged particles create their own magnetic field as they move through space, squashing the Earth's magnetic field, in places cracking that field, causing it to reconnect and allowing charged solar particles to make their way down the newly reconnected magnetic field lines towards the poles. Now, when that happens, you get amazing light shows given off, okay? You get it happening on the gas giants in our solar system. Here we have a video that shows real observations of the aurora on Jupiter. And the reason that you get the aurora, those high energy charged particles are able to, as they get absorbed by electrons in the atoms of the gases, those electrons gain energy from that charged particle that's collided with them, and they jump up to a higher energy level. We'll look at that in a bit more detail in a minute. As they lose that energy, because electrons are kind of lazy, the only way they can do that is by throwing out a little packet of energy. And it does that in the form of a photon or of light. Now, for the Earth, it's really clear to see our aurora are generated by solar particles. For Jupiter, it gets a little bit more confusing. Yes, the aurora on Jupiter are generated partly through interaction with the sun's charged particles, the solar wind, but also Jupiter has got moons like Io, highly active volcanic moons that are spewing charged material into its upper atmosphere. And that charged material, in the same way as the charged particles from the sun, can also interact with the upper atmosphere at the poles of Jupiter, triggering additional aurora effects. And this could be an explanation for why we're getting this methane being triggered and potential auroras on this brown dwarf star. Potentially, what we're seeing is the trace of an aurora that is being potentially, and I'm using potentially a lot because we've not been able to directly image it, but potentially that could be being triggered by a companion moon of that dwarf star. And that would be kind of weird, because the whole point of dwarf stars is they never were able to form, brown dwarfs, they weren't able to form into stars. We don't commonly see them with massive amounts of planets or things going around them. So this would be a pretty big discovery. And here you can see, again, the spectra that we got of this atmospheric methane that's linked to those aurora. And just for a minute, think about what this graph is showing us. This graph is showing us a plot of different wavelengths of infrared light. That's what we've got along the x-axis, the bottom axis. On the y-axis, the up and down axis, it's giving us basically the brightness, or how much of that light we're getting emitted in our direction. So we can see where we're getting large amounts of light that correspond to a particular wavelength, and therefore a particular, in the case of visible light, atom, and in the case of infrared light, molecules. And this means that we are able to fingerprint distant objects like this brown dwarf just by the light that reaches our telescope. We don't have to go there, we don't have to take a sample. We can use the light to fingerprint what we're looking at. It's an absolutely phenomenally powerful tool. So this is basically what we do. You have your distant object, light is carried from that distant object to your telescope. You can then split it into its spectrum, into its rainbow, but of different types of light. And then you can start to analyze that and have a look at the different wavelengths that you're getting a large intensity from. For visible light, this is what we end up getting. We call it an emission spectra, a series of bright lines that correspond to particular wavelengths. And those wavelengths are unique to each individual atom. So at the moment I'm using visible light as my example because it's a little more easy to understand. In this picture here, I've got a little diagram that shows some lines, and these are representing what we call energy levels. Now, even though it looks a bit like a ladder here, it's important to state that this isn't to do with a physical distance so much as it's to do with allowed energy. Depending on the charge and the size of the nucleus and the number of electrons that are orbiting that nucleus, orbital electrons have got particular energy states at which they're able to exist. Most of the time, an electron wants to be sat in the ground state, the chill state. But if an external charged particle does come in and impact that electron, it can transfer some of its incoming energy to that electron. The electron gets excited up to a higher energy state. And in order to be able to drop down again, it has to give off a little packet of light energy called a photon. Now, the energy of that photon corresponds directly to the difference in energy levels. The bigger the drop, the more energy that photon has. And the more energy a photon has, the higher a frequency it has. And that means the shorter a wavelength it has. And so as a result, each individual energy transition or drop will give a photon, a packet of light energy, of a different wavelength and a different frequency. And if you know that for this atom we have 14 possible transitions, and these are the wavelengths at which we can get that, you have a fingerprint for that atom. We can do the same with molecules. It's a little more complicated though. Molecules, you don't just have electrons going around. So this is where the infrared comes in. Molecules are constantly moving. Yeah, they're basically experiencing their own little molecule disco, and they can move in different ways. You have the traditional kind of twist dance that they can do. You have classic dad dancing. And each of those different modes of vibration, each of those different dance moves, for want of a better word, will produce photons of a particular energy and frequency. And it just so happens that either from those vibrations or as a result of absorbing and then re-emitting infrared radiation, the wavelength and the frequency that we get from molecules is in the infrared. And if you have more mass at the end of your disco, if you're holding a couple of weights while dancing, well, you're going to be a bit slower. The frequency of the infrared that is emitted is going to be lower. And so just as we can with the wavelength of visible light, we can use the wavelength of infrared light to tell us about what those molecules are. And we can get a spectral fingerprint for molecules as well as atoms. And that is what the Webb telescope is doing. That's how I can know that there's methane on a brown dwarf, and that methane might well be being triggered by an aurora that might be being triggered by a companion moon. All of this just from the infrared radiation that we are observing through the Webb telescope. Physics is awesome. I mean, technically, you could say this is a bit of chemistry as well, but I prefer to go with physics. So now moving on, we've looked at some of the strange things, but actually, potentially one of the biggest projects that the Webb telescope has been looking at is exoplanets. Now, an exoplanet is just a planet that orbits a star other than our own, a star outside of our solar system. And we've observed exoplanets before. We have had the Kepler mission, which has found thousands of exoplanets, and even the Hubble Space Telescope was able to observe some. And so in the short term, at least, the Webb telescope wasn't seeking out necessarily new exoplanets. It was taking that spectral sniffer dog equipment and pointing it at ones that we already knew existed. Because one thing we have struggled to do up until now is to get a reading of, does that exoplanet have an atmosphere? And if so, what is in it? Why does that interest us? Well, these are other planets. If they have an atmosphere, we want to know, is it similar to Earth's? Particularly if that planet happens to be within what we call the habitable zone of that star, the point at which you can get liquid water existing. So initially, at least, the Webb telescope has been tasked with looking at exoplanets that we already knew existed, studying the atmosphere, looking for an atmosphere and seeing what we could find. Now, exoplanets, we have a few different categories of them. And some of these are quite different to ones that we have within our solar systems. We have terrestrial ones, much like the Earth. We have super Earths. So basically, they are rocky planets but they're closer in size to something like Neptune than they are to the Earth. Then we have ice giants like Neptune, similar in size. And then we have gas giants like Saturn and Jupiter. But actually, the most common kind of exoplanet that we've observed so far is something called a hot Jupiter. Hot Jupiter gets its name from the fact that it's a large gas planet like Jupiter, often much bigger than Jupiter is. Hot because it's orbiting very close to its parent star. So close that hot Jupiters can have orbital periods of days or even hours. That's a year of just a couple of days, whizzing around its parent star. The reason why we have seen so many of them is they're big, they block a lot of light, and because they are so close, we get to see them with regular periodicity. We get to observe them very regularly. So what Webb did was it looked at some existing exoplanets that we already knew existed. The first one was WASP 39b, and this was an early release of information. WASP 39b is about 700 light years away from the Earth. It's roughly Saturn-sized, and we've known about it. It orbits much closer than Mercury to its own star. So if you imagine a gas giant the size of Saturn, but orbiting closer than Mercury is to our sun, to its star, that is a large planet with a very short time period. We know we're going to get good observations of it. And this was one of the first things that Webb actually looked at. And what we got from it was an absolutely exquisite spectral data set for this WASP gas giant. For the first time, we were able to confirm not only that it had a dense atmosphere, but by looking at those spectral infrared fingerprints, we could see sodium, water, carbon monoxide, carbon dioxide, sulfur dioxide. And so this was really proving what the capability of the Webb telescope was. Now, we know that humans couldn't live on this planet. It's far too hot, it's too big, and at that distance, there'd probably be some pretty hefty tidal effects as well. But this was a proof of concept that we could take Webb's spectrometers, aim them at distant exoplanets. Remember, this is 700 light years away. We're seeing this as it was 700 years ago. And we can figure out what its atmosphere is made up of. Phenomenally powerful. And then we have got K218b. This is about, I think, around 9 times as big as the Earth is. The reason why this is important is that we have found carbon-based molecules in the atmosphere of this planet, including methane. And if you've got a hydrocarbon-rich atmosphere, then you could be looking at a situation a bit like Titan, one of the moons of Saturn. You could have a source of potential fuels for the future. The reason why this one is interesting is that we're seeing hydrocarbon-rich atmosphere in the habitable zone of its red star. So in the area where you can get liquid water. This is also a lot closer to the Earth. This one is about 120 light years away. So it's closer to us, it's in the habitable zone, and it has a hydrocarbon-rich atmosphere. And this is what we're seeing here. You can see we've got the typical carbon dioxide, but then we've got methane. We even get dimethyl sulfide and other interesting materials within it. So Webb is really starting to figure out what's going on with these exoplanets, and we're really early on in its exoplanet run. What's probably most exciting in terms of exoplanet exploration is exploration of the TRAPPIST system, TRAPPIST-1. Why do planetary scientists get so excited about this system? Well, this system has got 7 roughly Earth-sized exoplanets in, 4 of which reside just about in the habitable zone of its star. So this means that we have 7 potential Earth candidates. TRAPPIST-1d is on the borderline, really, of being in the habitable zone, but we've still got 3 really good candidates. Now, we're really excited to observe this, and we've been kind of systematically going through them. It's easier to observe the ones that are closest because we can see them more often. So Webb Telescope has already looked at TRAPPIST-1b and TRAPPIST-1c. And I mean, unfortunately, it's told us what we pretty much knew already. It's close to the host star. There's not much of an atmosphere to speak of. Any atmosphere that would have been there has probably been, you know, close to boiled off by the star that it's going around. But what's really exciting is that over the next couple of years, Webb is now going to be turning its attention to those ones that reside within the habitable zone. We don't have the information yet about them, but if we find thick atmospheres, and if there happens to be oxygen or water vapor or nitrogen, then we're looking at a potential Earth-like planet, and that would be unbelievably exciting to planetary scientists, and maybe more importantly, to astrobiologists, people looking for life in the universe. So this is still to come. We know that we can observe these exoplanet atmospheres. We know that we've seen TRAPPIST-1b and c don't have a decent atmosphere to speak of, but the exciting planets are still to come in terms of observation. And this is actually an image of the first ever direct image of an exoplanet that Webb was able to take. Yes, it looks a little bit blurry, but you can see here that we are observing it in different wavelengths of light. So different wavelengths of infrared. We're seeing it there in NIRCam, and we are seeing it in MIRI. MIRI uses the mid-infrared, longer wavelength, so you can see there the resolution is less good. It looks more pixelated. The near-infrared is a shorter wavelength. We have a slightly less pixelated look. But here you're seeing an exoplanet with about 9 times the mass of Jupiter, orbiting a much larger, hotter star than our own. But to get a direct, resolved, individual image of that exoplanet is really exciting, because we're going to get more, and Webb is going to be able to provide them. So I'm looking at my time. I should hopefully be able to get through everything that I want to talk to you about and have a bit of time for some questions and discussion. We've looked at exoplanets. Be a shame not to look at what Webb's told us about our own solar system as well. And the solar system exploration is still quite early days in terms of what the Webb telescope is doing. And also, Webb hasn't given us any images of Mercury, Venus, or Earth. And that's all to do with Webb's location in space. So the Webb telescope, being an infrared telescope, has to be able to keep itself incredibly cool. In fact, we want its average temperature to be down at about minus 220 degrees C, even cooler for the MIRI mid-infrared instrument. So in order to do this, we had to send it far away from the Earth, shade it from the sun, and for MIRI, we actually had to use a space freezer, a cryo cooler, to cool the instrument down to just a couple of degrees above absolute zero. So we sent the Webb telescope to a special orbital point called the L2 Lagrange point. This is effectively on the opposite side of the Earth to the sun. And so it's useful because it means that the Earth itself, A, stays in direct communication with it, but B, acts a bit like a sun shield for the Webb telescope. In order to do this, and the reason for this is to do with planetary motion. Now, if you look at the orbits of the planets in our solar system, generally, the closer you are, the faster you're going to orbit around. And so planets on the inside track will get ahead of planets on the outside track. This L2 point is really important because normally, if you imagine the sun is at the center, the larger of the blue dots is the Earth and the smaller of the blue dots is the Webb telescope. Normally, you'd expect this to occur. The Earth is going to get ahead of the Webb telescope, and pretty soon you're going to lose that sun shielding effect. But at this L2 Lagrange point, you are just the right distance away from the Earth for the gravitational pull of the Earth to act almost like a leash pulling on the space telescope. And what that does is it forces the space telescope to orbit with the same orbital period as the Earth, keeping the Earth between the telescope and the sun. and acting as a constant sun shield. Now, the Webb telescope itself is actually solar powered. And so in order to be able to A, keep stable, and B, be able to generate enough power to run, it doesn't just sit there, it's in what we call a halo orbit. This means that it's stable around that L2 point. It's really difficult to push it off course. And it also means that it's orbiting in such a way as to kind of just get its solar panels to the edge of that shade region produced by the Earth, so it can still produce enough power to run. Now, being at this L2 Lagrange point on the other side of the Earth to the Sun means that if it was going to look at the inner solar system, at Mercury, Venus, and Earth, it would be looking at the brightest, hottest thing in our solar system, the Sun, and it would get destroyed. Its sensors would get completely overwhelmed. So instead, it's looked at every planet outside from Mars. Mars itself was quite difficult to image. Mars, being quite close to the Sun, is actually still quite hot by infrared standards. And so we do get a little bit of whiting out. But what's really nice is that different rocks will absorb and reflect infrared to different amounts at different wavelengths. So on the left-hand side here, we've got our NIRCam at 2.1 microns. On the right-hand side, we've got it at 4.3 microns. And what we're seeing here is we are seeing different levels of emission corresponding to different rocks. But because Mars is so warm, we don't get much more data than that. If we really want to see the cool images, then we need to go further out into our solar system. This is one of my favorite Webb images. This is Jupiter. And in this image, we're actually seeing quite a lot. We're seeing the ring structure of Jupiter. Saturn always gets lauded for its rings, but hey, Jupiter has its own ring structure. And the ice particles that are in that ring structure actually emit really quite brightly in the infrared. So we got to see Jupiter's rings in a detail that we'd never seen before. We also can see here the bluish tints that we have at the top in the pole and the bottom in the polar regions. These correspond to the aurora that are being generated at the poles of Jupiter, thanks to the solar wind and to its active moons. You can also see, we're getting to see some of the moons around there as well, emitting brightly. And if we zoom in a little bit closer to Jupiter itself, again, we're seeing interesting effects. This time we've tweaked the color that we're assigning to different wavelengths. So in this one here, the more reddish colors that we're seeing at the poles are showing us the auroral effects. Yellows and greens are showing us hazes in the upper atmosphere. And then the more bluer colors that we're getting are indicating more lower in the atmosphere effects and events. But what's really interesting is if you look at the great red spot, this really bright swirl on Jupiter's surface, that's because it's at a higher temperature than the rest of the clouds in that region. The physical motion of this storm that's been raging for hundreds of years is generating heat, and we're seeing that in this infrared image. We've got some brilliant images of Saturn. Now, Saturn itself, the planet, looks quite dim. That's because some of the molecules in Saturn's atmosphere are actually extremely absorbing of infrared. But the rings emit a huge amount of infrared. And that's what we're able to see here in absolutely beautiful detail, as well as some of the moons of Saturn. But for me, probably the most important images are the images that we get of our more distant planets in our solar system and of the moons of Saturn. So this is an image that is taken of Titan. Now, with Titan is a moon that has a very, very thick, dense hydrocarbon atmosphere. And looking at it invisible, you cannot see down to the center. However, looking at it in the infrared, we can start to peek through and see some information about the surface. You can see at the top there, that dark area is called Kraken Mare. It's a large basin structure, we believe, at the pole of Titan. And we can see that in the infrared. We can see some of the cloud structures. We can see atmospheric haze in Titan. and Enceladus. Now, admittedly, the image isn't as impressive as some of the images that the Cassini mission sent us. In the top left here, you can see an image of water vapor being spewed out of Saturn's moon Enceladus. But what the Webb telescope is able to do is it's able to look at this plume, and that's what we're seeing here. This bright area is that plume of water that's being spewed out from Enceladus. And the key thing is that the Webb telescope is able to analyze that plume. And what we want to see is what kind of water it is, what else is mixed in with that water. It's done one set of observations already, and it will be doing more going forward. If we look at the spectrum, here's what we are getting from that. We're getting lots of information about it from that plume, and we will get more and more information about that moon. Why is that important? Well, Enceladus is one of only a couple of places in the entire solar system other than Earth that we know there is liquid water of some form, even if it is below an icy surface. And then you've got this beautiful little picture. Look at it. That is Uranus. Doesn't look like how we imagine Uranus does. In all the images that we see in the visible light, we see a blue gas giant planet. But if I zoom in on that, we see that Uranus actually has incredibly beautiful ring systems. They might not be as big as Saturn's, but actually the stuff that they are made up of is particles of dust up to about 20 meters across. And we can tell that just by looking at it with the Webb telescope. And this is the clearest, most beautiful images that we ever got to see of Uranus's rings. So by looking at our most distant planets in our solar system, we're getting to get a new appreciation for them. We also got to see the moons around. And then all the way out to Neptune. There we've got little Neptune, also a ringed planet. So all of a sudden, by looking in the infrared, by using the Webb telescope, we are starting to get much clearer images of these distant planets. And they're really cute and they're really pretty. Now, on to the big stuff, cosmology. What have we found out from the Webb telescope from some of the observations of the very oldest galaxies in our universe? I've basically subtitled this, Are we going to have to rewrite all of our cosmology books? Because potentially so. So let's have a look at some of the oldest objects we have looked at so far. This is an example of one of the oldest, what we call dead galaxies. This is a galaxy where the star forming has basically stopped. It is no longer producing new stars. And this occurred about 13 billion years ago. So really relatively soon after the Big Bang. Now, we're not sure why that is. There should have been plenty of gas and material around at that time for more stars to be forming. The fact that some of the galaxies we look at from very shortly after the Big Bang are already showing as having died or having dead stars, it's interesting. We're not sure about what that mechanism would have been. We have been able to look a little bit further back in time than to 700 million years after the Big Bang. And as time progresses and as we take more observations, we will get closer and closer to potentially 200 or 300 million years after the Big Bang. And I cannot wait till we get to that point. Another weird thing that we found about some of these early galaxies is that some of them have got carbon dust in them. Now, again, that's strange because typically carbon can only be created by stars when they get towards the end of their life, by stars that are, going through those final death throes, burning fusing ever increasingly large materials together. To find carbon dust, graphite dust in really early galaxies, it's weird. And we're not entirely sure why that is. This is just another question that the Webb telescope is throwing up for us. We've also got a really good look at what the structure of early galaxies was like. Nowadays, when we look at galaxies, they are typically spiral, elliptical, or irregular. Yeah, so spiral like the Milky Way, beautiful curved arms, elliptical, basically squashed spheres, or irregular, a bit odd. When we look at the earliest galaxies that Webb's been able to see, they all look a bit like pool noodles, kind of squished, stretched out, almost like a cigar. And again, we're not entirely sure why. We have to rethink our understanding of galaxy formation, particularly early galaxy formation, to be able to give some physics that can explain all of this. Probably the most important and exciting / frustrating thing that's come out of Webb has been in trying to confirm what the Hubble Space Telescope observations have told us about the age and the rate of expansion of our universe. So when we're trying to measure our universe, when we're trying to gauge the expansion of our universe, how fast it's expanding, how long it's been expanding for, we use something called a cosmic ladder. What I mean by that is we look at objects quite near to us initially, things on the first or second rung of that cosmic ladder, in order to gauge how fast they're moving away from us. I'll look at how we can do that in a second, and it's all to do with the redshift. So a galaxy that's moving away from us, we've mentioned already, the light gets shifted out towards the red end of the spectrum. The faster it moves away, the bigger that shift is going to be, the longer the wavelength shift is going to be. In order to be able to trace that, we use the spectral lines of hydrogen, or a known element. By seeing how that spectral line has changed wavelength, we get an idea of how fast that particular galaxy is moving away. But how can we figure that out? How can we work out how far away this galaxy is? Well, to do that, we use something called a standard candle. And the two common ones that we use are either type 1a supernova. These are supernova where you have a dwarf star and a much larger star in a binary system. The dwarf star strips material off of the binary star, getting more and more massive until eventually it reaches a critical mass and it goes supernova. Why is that useful to us? Well, all type 1a supernova have a very similar, identical light curve. They peak at a similar brightness. But the further away they are, the less bright that light appears. And we understand the relationship that light follows. So if we know how bright it really is, and we can see how bright it actually appears, we can work out how far away that supernova is, and we can get our distance measurement. The other type of standard candle that we use for even closer to us is something called a Cepheid variable. These are variable stars that grow and shrink in brightness. And they do this very, very regularly. And we now know that there's a relationship between the period of getting brighter, dimmer and bright again, and how maximally bright that star is. And again, if we know how bright it should be, and we know how bright it looks, we can work out how far away it is. Now, this isn't new science. The Hubble Space Telescope has been doing this pretty much since it's been observing. But the results that the Hubble telescope was giving us were not entirely tallying or making sense with our understanding of cosmology and our understanding of the nature of the expansion of our universe. The big reason for that is the further away an object is, the harder it is to resolve, the more error you get in your understanding of its distance. So the Webb telescope has been pointed at objects that Hubble measured the distance to give a much more accurate set of results. And to give you an idea of this, the top, you can see the Hubble Space Telescope imaging a supernova, a Cepheid variable. In the bottom, you can see the same patch of sky as imaged by the Webb telescope, and we get much better resolution. This means that we are able to pin down that distance-speed relationship in much more detail than with Hubble. And it turns out the Hubble Space Telescope got it right, more or less. So we have to rethink our understanding of our universe, of dark energy to an extent. Maybe we need to now think about exotic dark energy, something that's even further increasing the expansion of our universe. But Webb has been able to confirm this and set us on the right path to figuring out exactly what is going on. To finish off with, then, I'm going to end up with some of the prettiest images that Webb has sent back to us. And these are images largely of nebulae. Nebulae are massive clouds of dust and gas. And again, here I'm zooming in just to show you, when we're looking at these objects, how small a patch of sky we're zooming in on. So here I'm zooming into a tiny little patch of sky, the Large Magellanic Cloud, a massive star-forming region, hundreds of thousands of light years away from the Earth. And we're still zooming, and we're still zooming, and we're still zooming. And there we go, getting there into our nebula. Now, this nebula is an enormous star-forming region that also has a huge amount of what we call cavities. So there are areas here that are looking much blacker, and that's where the stars have blown away that dust and that gas. And this initial image that we see here is using the near infrared. So this is allowing us to peek through that dust and gas at the star-forming cluster in the middle of this nebula. When I switch to the mid-infrared, I do get quite a different picture. This is the same region of space using the mid-infrared. You can see that the young stars that are being formed become less visible, but what we can see is we can see the filament structure of the gas. We can see the areas where we're getting gas clumping together into newly star-forming regions. And this is only possible because we can switch between the wavelengths of the infrared that we are looking at. We then have the Orion Nebula. And I won't zoom in on every one of these, but I do like the odd zoom in video just to, again, contextualize how small an area we are looking at when we zoom in on these things. So this is just another star-forming region, huge numbers of stars forming inside this dust and gas nebula. But what's really nice about this is you can see here how much improved our resolution is. This is a Spitzer telescope image of the a star-forming belt within the Orion Nebula. And this is a James Webb Space Telescope near infrared image of the same region. The black images in here, by the way, the black spots, they're not artifacts or anything like that. They are stars that normally would be so bright they would overpower the detectors on the telescope. So we use what we call a coronal blocker to cover them over so that we don't lose the sensitivity of the detector. And so again there, we're seeing this strange bar star-forming region in the Orion Nebula. One of my, and this is what we can see in the near infrared, so young stars that are forming within Orion. Absolutely spectacular. Probably my favorite area that was imaged by the Hubble Space Telescope is the Eagle Nebula, the pillars of creation within that. Now, the pillars of creation are really interesting because the stars that are forming are blowing the material out into these pillars. And as soon as we start looking first in the near infrared, and we can start to see all of those stars within that nebula, it looks purposefully ghostly here because it's been typeset in that way to allow us to see the stars within. And then if I switch to the mid-infrared, well, then it looks even more ghostly. Those stars disappear, but again, we're seeing the gas structure of those pillars within the nebula. This is an interesting one. This is a protostar that has already pretty much blown away and compressed away a lot of the gas in its star-forming region. This protostar is only about 100,000 years old. It's very, very young. And we can see filaments or tendrils of molecular hydrogen. They've been shocked by the pulsing of this protostar as it's blowing away and starting to get rid of the atmosphere around it, of the gas around it. That shock and that turbulence is what's inhibiting formation around the middle, which is why it's got that kind of hourglass shape. And what's really lovely is you can see right here in the middle, you've got what looks like a dark line running through it. That is an edge-on view of a protoplanetary disk. That is the area around this protostar that exoplanets are just starting to be born in. And this is pretty much what our star would have looked like at the beginning of its life. So we're kind of seeing our own solar system as it was. And this is just beautiful because I think it's incredibly pretty. This is the Small Magellanic Cloud, and I've just included it because I think it's an absolutely stunning, stunning image. Again, you have to give credit to visualizers, to the artists like Judy Schmidt, who assign which colors to attach to the various different molecules so that these are meaningful to us, so they tell us interesting things. So what's next? A lot of the same and some new things. For the period of July 2024 to June 2025, there are 253 general observation programs that have been selected for the Webb telescope. That includes more exoplanets. We are going to look at the TRAPPIST system in much more detail. We are going to look at a system called Kepler 167e, and we're going to see if we can identify exomoons. We are pushing the limits of the Webb telescope to the max to see, can we see moons around these exoplanets? We're going to be looking further back in time. We anticipate within the next year, we are going to go as far back as 13.5 billion years. We're really pushing the limits of how far back we're looking for. We're going to be studying supermassive black holes at the heart of giant galaxies. We are going to be looking at Enceladus's gas plumes in even more detail, figuring out what is in there. We are going to do the best study so far of Jupiter's red spot to analyze what its structure is, what the dynamics are, what the chemistry are. And we're going to be looking out for more lensed supernova and being ready to say, we need to point it at this right now to have a look at it. And that's just the next year. We have probably got another 15, 16, 17 years worth of amazing observations, amazing new science, and amazing images to come from the Webb telescope. And I'm definitely really excited about it. I hope you guys are too. I think we've just got time to look at a few questions there as well. I got through everything, Margaret. Yay! So let's have a look and see.
Yeah, so do you want to choose the questions, Sophie? There's quite a few.
Absolutely.
Oh,
that's interesting.
Yeah?
So one of the questions says, oh, go on.
I thought one, Mark, did you say that it was the question with Georgina Hardy? Did you say that it was possible to see the same supernova, both with the Hubble in 2016 and with the Webb in 2023? Could you explain how this is possible?
No, so the supernova that Hubble saw in 2016 was a different supernova to the 2023 one, but they occurred in the same galaxy, which is strange enough in itself. So the 2016 one we saw very late on in the supernova light curve. The 2023 one was a different one in a different part of the galaxy, but we got there a lot earlier with multiple views of it. We've got, if it has 4 cameras, does the radiation get split 4 ways, or is it only used one at once? Like it can be split. So you can even have, the Webb telescope has an innovative, basically a kind of like a light gate system. So it splits the detector up with little tiny magnetically controlled gates that can open and close. So actually it can look at multiple objects at once and select that it's only going to let the light in for that patch of sky and that patch of sky. And then you can choose from the optics which of the devices you want it to go through. You can look at the same object with all 4 of the detectors at once, all 4 of the devices at once, or you can say, I only really care what this looks like in the mid-infrared and have it go through that. So it really is like a Swiss Army knife. You can be very selective about what you are looking for. Why did 2 of the mirror segments look different even in their original state? So in that original state, the mirror itself is curved ever so slightly. So effectively the whole mirror is trying to become a parabolic mirror to be able to get a really good focal point. What you were seeing in that image there was effectively we're looking at reflections of infrared off of the mirrors to see how they're aligned, and that would just have been an angle thing with it. It's not that there's any specific difference, it would just be the tipping of the angle. They also use that to look at the alignment of the mirror segments as well. So the 4 modes of operation, it's basically 4 different wavelengths. So when we are looking at the information that we're getting from the light from these objects, different wavelengths tell us different things. And so the different detectors will be keyed in to look at particular wavelengths of light that are to do with maybe molecular emission, that are to do particularly, you know, we tend to get very strong emission here for water vapor and things like that. Different wavelengths, in order to be able to be processed, different wavelengths will actually diffract and get bent through the detectors and through. So let me see if I can get to a slide that gives you an idea of what I'm talking about on this. So I'm going to go back to the bit on that presentation. If I show you a picture of MIRI, it showed the inner workings of it. There we go. So if you have a look at this image here, what this is basically showing you is it's showing you the possible light paths, or the light paths that light going into the mid-infrared instrument will take. And you can see that we've got different colors of light represented within these bands. Those different colors are showing you the different wavelengths and how they will be reflected, refracted and diffracted to different amounts as they bounce around inside the detector there. And effectively what was happening is one of the modes of operation, or one of the keyed in wavelengths that we were particularly looking for, we weren't getting as much of the information through. It was like there was some kind of distortion or interference that was going on with it, most likely to do with some kind of internal alignment. How they fixed that with the programming, I'm not sure. I'm not a programmer, but I know that they were able to analyze where the difficulties were and figure out a workaround for it. Beyond that, I can't be any more specific, I'm afraid. That's not my area of expertise on that. Oh, could the JWST detect the heat signature of a bumblebee at a range of 250,000 miles? Now, heat signature, no, not so much. Thermal infrared is actually outside. It's even more outside than the mid-infrared is. If the bee were the only thing in space and there were no other sources of infrared, because warm object, it will still be emitting some mid-infrared, it will be still emitting some. If there were no other sources of heat, yes. But everything in space, if it's above absolute zero, is emitting some form of near infrared or mid-infrared radiation. And so you end up getting to a point where small signals do get swamped by everything else. What a great question. I love that. Answered that one. So I answered the one about the supernova. Oh, that's a good question about how far apart in time are the gravitationally lensed images. I'm not actually sure on that one. It wouldn't be more than about a day, because the kind of supernova light curves that we get typically go on for a few days, up to a week or so. So we are looking within that kind of day to week time frame. More specific than that, I wouldn't be able to say. Oh, that's a good one there. When scientists look at objects detected with the JWST, do they do it via images or via spectrum or something else? So depends on what they're looking for. Some of my former students are studying exoplanet atmospheres. They look at the spectra. That is what they're interested in. That is what they want. They will get that spectral information. They don't really care what it looks like. And we have to remember that the images that we get are not images in the sense that Hubble images are. We're basically getting a combination of wavelength and intensity data. So the way that a camera works on a telescope or even on your phone, you have a CCD, a charged coupled device. When a photon hits it, that triggers the release of an electron that gets stored at the end of your observing period. All of those stored electrons are allowed to run. They produce a little current, and that tells you how many photons have hit that bit of your detector. So when we are looking at images, we're not seeing them in the same way that we see visible light ones. We're getting a reading of how many photons of infrared of a particular wavelength have hit that point. However, when you then start keying them in, we know that, you know, hydrogen emits at this wavelength. So every time I see a photon has hit my CCD of that wavelength, I'm going to color that red. That's when we start to form the images. So if you are looking for exoplanets, you're interested in the spectra. If you are looking at protoplanetary formation, then you're going to look at the spectra, but you're also going to want to have a look at what those images that you've produced are, because that's giving you information about the structure of the gas clouds. It's telling you where you're getting the hot areas, where we're getting star formation and things like that. So you really do use a combination of all of it. And the important thing is as well, if I'm a scientist and I've put in for time to look at this particular object and I only want the spectra, well, I've still got the images as backup. Somebody in the future can turn around and go, actually, we've still got more information that wasn't studied at the time on this part of space. And this new telescope has found something interesting over there. So let's dig back in to the old Webb data. We do that all the time with old telescope data. Even today, we dig into 20, 30-year-old data because we've discovered something new and we want every possible piece of information. Can Webb resolve any surface detail on nearby exoplanets? No. You saw the image of the exoplanet that it directly imaged, and it did look like pixels. These objects are very, very far away. And the other thing is, because infrared has got a longer wavelength, we will never be able to resolve to the same kind of detail that we can resolve in visible light. All of these exoplanets are outside of our own solar system. So it does get very, very difficult to resolve that. If one happened to be closer, or, you know, maybe in the future, if we scale up to even better telescopes, that might be possible. But for the moment, with the Webb telescope, the exoplanets that we're looking at are never going to be particularly detailed in how we see them. And answer a couple more, because I know I'm overrunning, Margaret, and I don't want to keep you for too long.
Okay.
Do we take account of the atmospheric composition of a planet when we calculate whether it's in the habitable zone or not? So to an extent, you have to after the fact. The initial habitable zone is literally, we are looking for the region around a star. We know a star of a particular size will be emitting light and heat with a particular intensity. We understand the inverse square law nature of that light, of that radiation. And so if we know we've got a red dwarf star of this size and this luminosity, we know that liquid water, in theory, is able to exist in this range here. Now, where things do get interesting is on the fringes of that. You could have a planet that is towards the cold end, or maybe even out of the habitable zone as we understand it just from the radiation properties. But let's say it was a planet like Venus that had a very thick carbon dioxide atmosphere that was acting as a runaway greenhouse effect, then yeah, you could have that planet just outside of the habitable zone still be hot enough for liquid water to exist. So once we've got the habitable zone mapped out, we have to then start taking into account the compositions to go, well, have we got some outliers that are, you know, still candidates, even though they're right on the fringes there of that.
I think
if there's, and this will probably have to be the last one, I think, Margaret,
Yeah.
if that's all right.
I wondered about this one about if
I would love to answer questions all night.
If there's been so much improvement from Hubble to
Was that Margaret?
Yes, that one. What would be the future massive space telescope be like? What do you think you could hope to see with the
so we're kind of seeing it already. We're seeing some of them already. So some of the things that we're seeing that are very exciting to me at the moment, things like the square kilometre array. So instead of having one big telescope, let's have hundreds of smaller telescopes that are observing in radio in longer wavelengths. And because we're using longer wavelengths, we can have them all spread apart so that they act as one giant telescope. You know, once we start to understand how different wavelengths can be observed, then we can start to plan our telescopes out. There is no doubt in the future, if we could build a bigger infrared telescope, we'd be able to get even better resolution. We'd be able to look further back. If we could build a bigger optical telescope, if we could take a telescope like the Very Large Telescope and stick that in orbit in space, oh boy, that would potentially knock elements of Hubble out of the water. But the problem is, the bigger we build them, the harder they are to launch, and the more likely they are to get damaged or to get warped under their own weight. So we're getting close to, with current technology, about as good as our space telescopes can get without further improvements in the actual optics that we're using and the devices that we're using. The really key thing is things like the spectrometers that we're using. So things like MIRI and devices like that, and the spectrometers, the way that we can analyze the spectra, these are devices that 25 years ago would occupy an entire room. And they've been miniaturized and shrunk down to be able to fit on these space telescopes. And as that technology gets better, then actually our telescopes are going to get better, and what we can image and what we can do is going to get better as well.
Thank you, Sophie.
Brilliant questions. Absolutely love the questions.
You've blown most of our minds, certainly blown mine. So I hope you have a good time next year, finding out even more. And maybe in a year or two, we can have you back. So thank you very much.
Absolutely.
Yes, thank you. And could I just have a plug for our next Hereford and Worcester lecture, which is on the 7th of May, and it's Greg Adamiak, who's going to talk to us from Poland on using thermoluminescence, which can actually tell us whether ceramics are forges or not. So don't forget to register for that. And thank you so much, Sophie. And good night, everybody.
Thank you for having me. And thank you for your questions, everyone. I hope that's been interesting.